Hello everyone, I am Honar Gupta. I am a PhD student at IIT Kanpur. Today I will discuss about what was taught in the week 2 of the fundamental of supersonic and hypersonic flow. If someone has any question, they can ask and they can open the mic and speak also. And if in the week 1 also there was some doubt, they can also ask. So in the week 2, mainly the tensor notations and some vectors and small patterns in theory and neighbor explications were discussed. So we will start with the tensors. And in the tensor, we will study the initial notation. Using the initial notation, we can write the long equation in very short form. So let's say there is some vector x in xyz plane, and it is given by x1 I cap plus x2 j cap plus x3 k cap. And we can write x1, x2, x3. We can write this vector as I, j, k also e1 cap, e2 cap and e3 cap. And we can simplify it as xi, ei cap, where I will be from 1 to 3. So it is implicitly expressed that I will be equal to 1, 2, 3. These are the dimensions. And if there is one indices is repeated again, then it is addressed as a sum. So the minimum number of directions required to represent a vector is called the basis. So in this equation, our bases are e1, e2 and e3. Let's see an example. There is one b vector u1 e cap, e1 cap plus e2, e2 cap plus e3, e3 cap. This is a first order tensor. So we can write it as ui ei cap. You might have heard about the stress tensor sigma ij. It can be written as sigma 11, sigma 12, sigma 13, this matrix form. And this is a second order tensor. In this one, first indices represent the direction of the surface normal. Let's say this is the surface. This is the surface. Then this represents the direction of the surface normal. So this is the I indices, and in this surface there might be three different stress, one normal and two tangential. So both are, so second indices represent the direction of the stress. Regarding notation, there is one Einstein summation convention. Whenever there is one indices which is repeated in a term, then summation over this is implied. Let's say this is the dot product x vector dot y vector equal to xi by I. So it means that we are summing each and every term. We are summing for I equal to 1 to 3. So it can be written as sigma x1 y1 plus x2 y2 plus x3 y3 after summation. Let's say there is some yi which is given as AIM BM. So here M is being repeated. So the summation will be from M equal to 1 to 3, which can be written as AI1 B1 plus AI2 B2 plus AI3 B3. The summation will be applied only when this indices is being repeated in a single term. How to manipulate using the indicial notation? First is the substitution. Let's say AI is given by CIM BM and BI is given by SIM DM. This B is the same, so only indices are different. So we will substitute the indices. Now see that in the I there is already one M present. So we cannot directly write this as BM equal to SMM DM. First we have to change this M indices to some other indices. So BI can be written as SIN DN. We have changed this M indices to N. After that only we will change this I indices to M. So it will become BM equal to SMN DN. Now we can substitute this BM2 in this AI. So AI will become CIM SMN DN. Second is product. Let's say there are two quantity S equal to AM BM and R equal to XM YM. If we have to do the product of S and R, so first whenever we are doing product of two different quantity, we have to write both quantity in different indices. This quantity S is in indices M and this R is in indices M, so we have to write in some other indices. So we have written this, we have changed this M to N, so it will become XM YM. And now we can do the product. Is there any doubt till now? Then now we'll see the Kronecker delta. Kronecker delta is an operator, not an operator. It is a, you can say, identity matrix in a simple form of order 3. So it can be written by dot product of EI cap dot EJ cap. So dot product will be 1 only when both I and J are equal. And if I and J are not equal, then it will become 0. There are some property of it, like we can interchange the indices del ij equal to del ji. If we multiply two indices, two Kronecker delta del ij into del jk, which have same one index as the same, so we can remove that indices and become del ik. And if we multiply two Kronecker delta del ij into del kl, then we cannot change the indices, interchange the indices. If both indices are same, del ii, then as mentioned before, that it will be the summation. Del ii will be the summation I equal to 1 to 3. So it will become del 11 plus del 22 plus del 33. And del 11, del 22, del 3 are both 1, so it will become 3. If del ij is multiplied by some vector uj, then the indices of this uj will change to ui. You can prove all these properties also. there is another one symbol, Levy-Civita alternating symbol or permutation symbol. It is given by epsilon ijk, and we can find it using the triple product ei cap dot ej cap cross ek cap. So from the triple product we know that its value will be equal to 1 when I, j, k are in cyclic order. When they are in anti-cyclic order, then its value will be -1. And if two indices are same, then it will be 0. Let's say they are E1 dot E2 cross E3. Then you can see that they are in cyclic order 1, 2, 3. Then it will equal to 1. If it is in anti-cyclic order, then it will become equal to -1. And if any two of the symbol I or the indices are same, then it will be equal to 0. There are also some properties of this Levy-Civita symbol. If you multiply two of the symbol with one indices same, FLM IJK into FLM IMN, then it will become equal to delta JM into KN minus JN into KM. And if two of the indices are same, then it will become equal to 2 into delta Kn. If all the three indices are same, then it will become equal to 6. You can put directly this n equal to k, and you will get del kk equal to 6. And if epsilon ijk is multiplied by del jk, then it will become equal to 0. These are some properties. These properties can be used whenever we are using the vector multiplication or tensor into vector multiplication. Now we will write the dot product in the initial form. Let's say two vectors are a vector and b vector. A vector can be written as ai ei cap, and b vector is bi ei cap. If we do the dot product, then we have seen that for the product we have to change the indices for one quantity. So we have changed the indices of b from I to j. So it will become ai ei cap into bj ej cap. So we can multiply ai and bj because they are only scalars only, and this ei and ej both are vectors, so we have to take the dot product of them only. And ei dot ej equal to del ij, so it will come ai bj del ij. Now if we remember the properties, del ij into bj, it will become equal to bi from its property, so it will become equal to ai into bi, and it can be written as the summation a1 b1 plus a2 b2 plus a3 b3, which is a scalar. Similarly, we will see the vector product. If two vectors are there, a vector, b vector, for the vector product we have changed the indices for one vector and we have multiplied. So ai and bj are scalar, so it will come out, and ei cap and ej cap, we have to do the vector multiplication for them. And from the properties of Levy-Civita symbol, this ei into ej equal to epsilon ijk into ek. So we can substitute it here and we'll get this. We can either write the some vector quantity like this, its scalar value and its direction, or directly like this quantity. Here you can see that if we are writing like this, you can see that I is being repeated, j is being repeated, but k is not being repeated. If some indices is coming only one time, then it is not a scalar generally. It is either vector or it can be tensor also. Here only one indices is not being repeated, so it is first order tensor. If there were two indices which were not being repeated, then it might be second order tensor. You might have seen this del symbol, which is called the vector differential operator. It is given by I cap dou y dou x plus j dou y plus k dou y dou z. This I can be written as e1, j e2 and k e3, and similarly x2 x1, y2 x2 and z2 x3. So it can be written as like this, and in the simplified form, in the field notation, it can be written as ei cap dou y dou xi cap. So using this operator, there are some vector quantity which are defined. One is the gradient. It is done on the scalar value, scalar field. So if there is some scalar field phi, we can find its gradient using the del operator. Del phi equal to ei cap dou y dou xi. We have directly used this ei cap dou y dou xi, and our field was phi. So it will come like this, and if we expand it, then it will come I cap dou phi by dou x, j dou phi by dou y, and k dou phi by dou z. This is a vector quantity. So what does gradient signify? So it finds the maximum rate of change and its direction. Let's say if there is one field phi and this line is phi equal to constant, then this del phi will give the maximum rate of change and its direction, in which direction it will be the change in phi will be the maximum. We can find its directional derivative in one specific direction also. Let's say there is this s cap. So this dou phi by dou f will be given by del phi dot s. Okay, this question was in the last year's problem. If the pressure field is expressed as P xyz equal to 2x square plus 4y square minus 3z square, the expression for del P is given by. So we have seen del P is what? I dou P by dou x plus j dou P by dou y plus k dou P by dou z. So we have to find these three values. So dou P by dou x will be 4x, dou P by dou y will be 8y, and dou P by dou z will be minus 6z. So we can substitute it here and we will get 4xi cap plus 8y j cap minus 6z k cap. C is the answer. So if in some question you have to find the gradient or derivative, you can directly use this formula for gradient. using this vector differential operator, we can find one more quantity which is divergence. Let's say one vector velocity is given by ui ei cap, then del dot b cap will be given by ei cap dou y dou xi dot uj ej cap. We have to change the indices because this is some other vector. Uj, so this derivative will be for this uj, and ei and ei dot product will be for this ei and ej. So dou uj upon dou xi ei e1 ei cap dot ej cap. This will be written as del ij. So now if you see this del ij, we can change the indices for this j u, because this indices is being repeated. So it will become dou ui upon dou xi, and it can be expanded dou ui upon dou x1, dou u1 upon dou x1 plus dou u2 upon dou x2 plus dou u3 upon dou x3. So we have seen this already. The expression dou ui upon dou xi for 3D Cartesian coordinate is given by. So what is the answer for this? Just now we have expanded it. So we can expand it by dou u by dou x, dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3. x1, x2, x3 are nothing but x, y and z, and u1, u2, u3 are u, v and w generally. We take velocity as ui cap plus vj cap plus w k cap. So this b will be the answer. A velocity vector field is given by v vector equal to 5 yz I cap plus 3 xyz 3 xz j cap plus 4 xy k cap. Then del dot b vector is given by. How to find the del dot b? Does anybody know? We have already talked about it. So it is very simple. This is u1, this is u2, this is u3. So we can directly use dou ui upon dou xi. If we use this, then we can find the answer for this. This is a very simple problem. I think similar type of problem is also in assignment, so you can solve it. Now we will see what is the curl of vector field. If velocity is given by ui ei cap and del is given by this, then del dot v will be like this. We have changed the indices for this v, and now if we multiply these two together, then this will be del uj upon del xi, and this will be ei cross ej. This ei cross ej is epsilon I j k into ek. From the definition of this alternating symbol. So we got this. Now if you see this epsilon I j k, we can change the indices in the cyclic form. So if we change I to j, j to k, and k to I, its value will remain same, nothing will change. So we have changed it like this. Now we will see the line integral. Does anyone has any doubt till now or any question? Okay, then let's see the line integral. Let's say there is one open curve and there is one vector a vector, and on this curve, this along this line there is one vector. At this point there is vector n cap and its length is ds. Then this line integral is given by integration a to b a vector dot ds. This is for the open curve. Similarly, for the closed curve, for anticyclic, it is given as a positive integral. So it is given by a vector dot ds vector on the closed curve. For closed curve, this symbol is given like this. Now if you see that this is the dot product of two vectors, so it will come as scalar. So the line integral is a scalar quantity. Now if we have one open surface, or we have one closed surface which will make a volume, and this open surface is given by S. There is one small surface ds on top of it with normal n cap, and let's say there is quantity, scalar quantity rho on it and vector quantity v. Then the surface integral can be given as in three ways. So if quantity is scalar, then it is given by double integration p ds. If quantity is vector, it can be given as two ways. One is the dot product and one is the cross product. So it will be double integral v dot ds and double integral v cross ds. For both open surface and closed surface, it is given similarly. Only for closed surface, the surface is closed and makes a volume. So now if we see check if which quantity is scalar and which is vector. So what will be this quantity, scalar or vector? Double integration pds. It will be scalar or vector quantity. If you see that this p is scalar and ds is vector, so this is vector quantity. This v dot ds, this is the dot product of two vectors, so it will become scalar quantity. And this is v cross ds, cross product of two vectors, so it will be vector quantity. Another integral is volume integral. In volume integral, let's say there is one arbitrary volume v and there is a small element whose volume is dv, and there is one vector a vector and quantities and some other scalar quantity rho. Then this volume integral can be given as two ways. Triple integral rho dv, this both quantity are scalar, so it will give scalar quantity. And another is triple integral a vector dv. This a vector is vector quantity, so it will give vector quantity. Now, in many cases, we will find the combination of line integral or surface integral and volume integral. So, sometimes we need to interchange this integral to one another. So, there are some theorem for that. The first one is the Stokes theorem. This Stokes theorem convert line integral to surface integral. If there is one surface which is enclosed by one curve, there is one surface S which is enclosed by one curve C. So this C curve is one closed curve, and there is one ds, a small surface which has a normal at n cap direction. And if line integral of any vector quantity is given by integration a dot dc. One thing to pay attention is that this integral should be on the closed curve, and this closed curve should make this surface. Then this line integral will be equal to double integration del cross a dot ds. So we have to take the curl of this quantity and multiply with this surface. Take the dot product. So if you see, these both quantities are vector and this dot product will be scalar. If you see this right hand side also, this quantity is vector, cross product, this is also vector, and the dot product will be scalar. This is a one important theorem, so it will be better to remember it. Second theorem is Gauss divergence theorem. This theorem is for converting surface integral to volume integral. So let's say there is one closed surface which makes a volume V, and if we take a infinitely small element whose volume is dV and one surface whose area is ds, then for any vector quantity a vector, the surface integral is given by double integral a vector dot ds, and it can be written in the volume integral if we take the divergence of this vector del dot a dv. So if you see this in the left hand side, this is quantity is scalar. This is a dot product of two vectors. In the right hand side also, this del dot a is divergence. Divergence is scalar. So this quantity is also scalar. One thing to note is that this surface integral should be on the closed surface, and this volume for the volume integral should be made by this closed surface only. Only then this Gauss divergence theorem can be applied. There is one more gradient theorem. It is also for some surface integral to volume integral, but the Gauss divergence theorem was for the vector, and this is for scalar. So let's say there is one scalar quantity whose surface integral is given by rho ds, then its volume integral will be equal to del rho dv. This is the gradient of this quantity rho, and same this would be the closed surface, and this volume should be made by this closed surface. Left hand side this quantity is vector, right hand side is also this gradient is vector. Is there any doubt till now or any question? Okay, then now we will go to the fluid mechanics, and now we will see what is the continuum flow. So in continuum flow, when mean free path of the molecule is very less than length scale of the region of interest, then flow appears to be a continuous to this region. What is the mean flow path, free path? Mean free path is the distance between two consecutive collisions of the molecule. Let's say there is one molecule, it is moving randomly, and there will be collision with other molecule. Then between two collisions, let's say it collided here, then it will go here, then it collided another molecule. Then the distance between two consecutive collisions is called the mean free path. If this mean free path is very less, it is very less than length scale of the flow or body, there is some body, then body lambda is very less than L, then it is called continuum. Then we apply the continuum hypothesis. So let's see this region of a space where these particles are very far away to each other. So if we wanted to find the density of at one point, for finding the density we have to take the limit of del m by del v, and del v should tends to 0. It should be as small as possible. So at one point if we wanted to find the density and we took the small volume, then we might get the density as 0 also for this rarefied flow. So we cannot apply the continuum hypothesis here because molecules are very far away to each other, density is very less, and if density is high, there are very molecule and mean free path is also very less. Then if we see a region and we take a control volume, let's say, and we wanted to find the density at that point, and we started reducing the volume of that region, then at one point we will see that there is no change in density and there is one minimum volume at which this density will remain constant. So we take that volume as the volume of the particle. So generally the particle size is in the continuum hypothesis is taken as that only. So we have to assume that in the continuum flow, that flow is always continuous. At every point there is fluid present, and properties can be defined at every point. It should not be like at one point we cannot define the properties, like in rarefied flow some point we are not able to define the density, but it should not be like this in the continuum flow. For finding the fluid motion, there are two descriptions. One is the Lagrangian description and another is the Eulerian description. In Lagrangian description, fluid particles are followed as they move through a flow field. So let's say there is this one fluid particle and it is moving through a field. Then we follow this fluid particle. Let's think like we are standing on this fluid particle and observing the flow. Then this is called the Lagrangian description. In the Eulerian description, we observe from a fixed coordinate frame of reference. Let's say we are standing here at a fixed location and we are observing the movement of this fluid particle. This is called the Eulerian description. So we can change from one description to another description, and let's say if there is one property phi which evolves with respect to x, y, z and t, then the total derivative of this phi d phi by dt is given by dou phi by dou t plus v dot del phi. This d phi by dt is given in the Lagrangian description, and this is given in the Euler description. So from changing from one description to another, we use this substantial derivative. This is called the substantial derivative. There are streamlines which are present in the flow. So we define what is a streamline. A streamline is defined as a line which is everywhere parallel to the local velocity vector v vector equal to vy cap plus vj cap plus wk cap. So it is a line which can be made by joining the point which has the velocity tangential to that line. So let's say this is the streamline. So at every point of this streamline, velocity will be tangential to this line. So if you want to find the equation for this streamline, let's say there is a small element ds on this line which is given by dxi cap plus dyj cap plus dz k cap. So as we know that in the streamline, this direction of ds is also this. So as we know that this ds and v vector are in the same line. So the vector product of these two will be 0. If we take the vector product of these two, we will get w dy minus v dz I cap plus u dz minus w dx j cap plus v dx minus u dy k cap. So and this will be equal to 0, and for it to be 0, all individual terms should be 0. Which means w dy minus v dz, u dz minus w dx, and v dx minus u dy equal to 0. And if we equate these three to 0, we will get dou u by dou x equal to dou v by dou y equal to dou w by dou z. This is the equation of streamline. There are some properties of streamline. Flow boundary is always composed of streamline. Flow boundary is always composed of streamline because fluid cannot pass through the streamline. Because let's say fluid is passing through a streamline, then its velocity would not be along the streamline, which is not possible. So at the streamline, velocity is always along the streamline. So it will always meet the boundary. Two streamlines never cut each other. If two streamlines will cut each other, then at the point of intersection, there should be velocity in two directions, which is not possible. There is never flow across streamline, same point. For continuous flow, all streamlines extend from minus infinity to infinity or form a closed curve. So for continuous flow, either streamline will become a closed curve or it will extend from minus infinity to plus infinity. There will not be end of streamline. For the governing equation, there are some important terms also, like angular velocity and vorticity. Let's say there is one fluid particle. This is one fluid particle, and at point A it has velocity u and v. Point C, its velocity will be given by v plus dou v by dou x dx, and at point B its x say at time t. At time dt, it will deform due to this velocity and rotate. Let's say this is a fluid particle, then due to the motion of fluid particle, it will rotate also, deform also. Generally, fluid particle does not only translate, it rotates also and deforms also. So due to its velocity, this C point will come here and D point will come here. So that's it. This line AC is rotated by angle delta theta 2 and this line AB is rotated by angle minus delta theta 1. So if we see the rate of change of this delta theta 2, d theta 2 by dt will be this height upon this length, which will be which will be dou v by dou x. This delta theta 2 is nothing but dou v by dou x dx dt upon dx, and if we take the its change, then it will become dou v by dou x. Similarly, dou theta 1 by dou t, d theta 1 by dt also. So if you want to define the angular velocity of this particle, then it will be the average of angular velocity of AB and AC. Angular velocity of AB is d theta 1 by d theta 2 by dt, and angular velocity of AB is d theta 1 by dt. So its average will be 1 by 2 dou v by dou x minus dou u by dou y. Here this minus is taken because this angle is negative. Similarly, this is for 2D, dou z. Similarly, if we see for 3D, we will get the omega x and omega y also. And if we see this omega x, omega y and omega z, it can be given by half of the curl of velocity. And we define verticity from using the curl of velocity. So verticity is given by curl of velocity, which is nothing but 2 times of the angular velocity. So if there is no angular velocity in the flow, then it is called rotational flow. It means curl of velocity is 0, it means flow is rotational flow. And if curl of velocity is not 0, it is called a rotational flow. There is also a strain of fluid element. This is AB, AC. This AB was rotated by delta theta 1 and AC was rotated by delta theta 2. So strain will be given by delta theta 2 minus delta theta 1, which is the total angular deformation. So its space is given by F directly proportional to strain, but here generally there is motion of the fluid, so we check it using the time rate of strain. And this time rate of strain is given by epsilon. So epsilon xy equal to d theta 2 by d theta 1 dt minus d theta 1 by dt. Similarly, we have taken the derivative of this. D theta 2 by dt is given by dou v by dou y, and d theta 1 by dt is given minus dou v by dou y. So it will become like this. Similarly, for epsilon by z, it will become dou v by dou z plus dou w by dou y, and epsilon xz equal to dou u by dou z plus dou w by dou x. This will be useful now we will see the governing equation, navy equation. First is the continuity equation. We have seen that there are two frameworks. There are two frameworks of finding the flow. One is the control volume, finite control volume framework, and one is the infinitely small fluid element. One is the control volume. This control volume is like this. This is the volume V, and there is one surface ds, and on this point velocity V is on the V. So continuity equation is given by this equation. In this equation there are two terms, dou y dou t, triple integration rho dV, which is nothing but time rate of change of mass inside control volume, plus double integration rho b dot ds, which is net mass and efflux through control surface. So what is this? Telling that whatever mass is thrown out of this control volume and is equal to mass generated inside the control volume. Now, since CV is fixed, control volume fixed, this limit of integration for volume integral are time invariant. Whatever limit are there for the control volume, this does not change with time. So this derivative can be taken inside and it becomes dou by dou t d. And for the second term, if we see, this is the volume integral and this is the surface integral. So we will also convert the surface integral to volume integral because this is closed surface. So surface integral can be converted using the divergence theorem. So it will become rho v del dot rho v vector d. We can substitute this both inside the equation and it will become like this: triple integration dou by dou t plus del dot rho v vector. dv we have taken common, and for it to be 0, it should be 0 for each and every point to satisfy the continuity. So it will be 0. So we got this equation dou by dou t plus del dot rho v vector. This is for infinitely small fluid element form. Generally we get differential form of equation. This is the differential form of equation. Generally we get differential form of equation using the infinitely small fluid element, and we get the integral form of equation using the finite control volume framework. Is there any doubt till now? Okay, then now we will, this currently is Eulerian framework. This is using the Eulerian description. Now we will change this to Lagrangian form. So there is one vector identity, del dot rho v vector equal to rho v del dot v vector plus v dot, this is del rho. We will substitute it in the equation, so it will become dou by dou t v dot del rho plus rho del dot v equal to 0. If we see the definition of substantial derivative, dou rho by dou t plus v dot del rho, it will become d rho by dt. So our equation will become d rho by dt plus rho del dot v vector equal to 0. This is the equation in Lagrangian infinitesimal fluid element form. This is the differential form of equation. For the steady flow, its derivative will be 0. So if we make this derivative 0, our equation will be del dot rho v vector equal to 0. For incompressible flow, this d rho by dt will be 0. This will be 0. So equation will become del dot v equal to 0. These are some forms of this equation. Now we will see the momentum equation. Similarly, if there was control volume as same as before, these are the steam lines. This is small elemental volume dV, and there is one surface small ds with end cap normal, and velocity is given by v vector. Density is rho. Then momentum equation is given by this equation. This momentum equation is nothing but F equal to m. Rate of change of momentum is, or you can say dp by dt. Rate of change of momentum is equal to force. So on the left side, this term, first term, is nothing but rate of change of momentum is control volume. The second term is net momentum efflux from the control surface. Whatever momentum is efflux from the surface. This third term is the surface force. Force due to the, this is the surface force. And the fourth term is the body force. Body force like gravity, magnetic force, or some other force. The surface force is like stresses, normal stress, shear stress, this and pressure, these comes under the surface force. And the surface force is given by this term. And this one term is sigma ij. Sigma ij can be given by minus p dou ij plus tau ij plus lambda kk del kk dou u kk upon dou x kk. This tau ij is given by this term mu dou ui upon dou xj plus dou uj upon dou xi. If you see this dou u kk upon dou x kk, it is nothing but divergence of velocity. So it can be written as this form also: minus p dou ij plus mu dou ui upon dou xj plus dou uj upon dou xi plus dou ij del lambda del dot v. We find the normal stresses sigma xx, sigma yy, and sigma zz. This for I equal to j, it will become 1. This will also be 1. So, and dou ui upon dou xt, these two will be equal. So, for normal stress, it will be minus p plus 2 mu upon dou ui dou x plus lambda del dot p. Similarly for sigma yy and sigma zz. Is there any doubt till now? Okay. So now we will see what is the mechanical pressure. Mechanical pressure is nothing but negative of average of all these stresses. So the sum of these three stresses is given by minus 3p plus 2 mu upon 3 lambda del dot p vector. If we take the sum of these three, this will become minus 3p, this will become 3 lambda del dot p, and this will become 2 mu dou by dou x plus dou b by dou y plus dou w by dou z. This is nothing but del dot p. So we can take del dot p common here. So it becomes 2 mu plus 3 lambda. If we divide it by minus 1 by 3, it will become p minus lambda plus 2 mu by 3 del dot v. And it will be p minus p bar equal to lambda plus 2 mu by 3 del dot p. So from this equation we can see that this is the thermodynamic pressure. P is the thermodynamic pressure. And P bar is the mechanical pressure. So the difference of this mechanical pressure and the thermodynamic pressure is not zero, which is equal to lambda plus 2 mu by 3 del dot P. And this lambda plus 2 mu is given by mu bulk. And generally for many material it is given back that this mu bulk is equal to 0, but it is not for every material, but for many material this mu bulk is equal to 0. So this P is equal to P bar, or lambda equal to minus 2 mu by 3. The result, if in this governing equation, momentum equation, we put tau ij equal to 0, then equation is called Euler equation. If tau ij equal to 0, then sigma ij is equal to minus p del ij plus del ij lambda del dot b. If we substitute this in this equation, then we will get the Euler equation. For the inviscid flow, this lambda will be 0. So our equation will become dou by dou t triple integration rho b vector dv plus double integration rho p vector dot ds v vector equal to minus double integration p ds vector plus triple integration rho f vector dv. So this equation also we can write in the differential form. So like we have seen before, this control volume is fixed, then this limit will not depend on the temperature. So we can write this first term dou by dou t triple integration b rho b dv equal to triple integration dou by dou t rho b dv. Before writing this, I think it is better if you see this momentum equation, this is the vector equation. So we can take first x momentum equation only. So for x momentum equation, it will become dou y dou t triple integration rho u dv, where this v is volume, plus double integration s rho v dot ds u equal to minus double integration p ds dot I cap plus triple integration v rho fx dv. Now it is like I told for dou y dou t triple integration rho u dv. It will be equal to triple integration dou y dou t rho u dv. The second term is the surface integral. We can write it is in volume integral using the divergence theorem. So it will become rho u v vector dot ds equal to triple integration del dot rho u v vector dv. This is also in the surface integral, so we can also write this in the form of volume integral. So I dot ds equal to triple integration dou py dou x dv. I have directly multiply it with the operator. This is only we have to take only the I component, so directly I have taken the I component of this. The last term of volume will keep the same, so our equation will become triple integration dou y dou t rho u dv. We'll take dv common also. Plus del dot rho u v vector minus dou py dou x minus rho fx. So this is plus dou py dou x minus rho x dv equal to 0. So this term should be 0 because it should satisfy at each and every point. So we will get dou u by dou t plus del dot rho u p plus equal to minus dou p by dou x plus rho fx. This is the momentum equation for infinite in the differential form. This equation can also be. Now we will see the energy equation. We will see the energy equation. This is the energy equation. There are 4 terms. First term is the rate of change of energy inside the control volume. Second term is the net energy efflux by the control system. This third term is the work done by the surface force. This fourth term is the internal heat generation. And this fifth term is the work done by the body force. Here in the equation, E equal to E plus Uy square by 2. So now we have seen all the Dodge equations. These are the Dodge equations. If all forms are put together, you might have seen this in the lectures also. So in the Eilerian form, infinitely small fluid element, this is dou, it is in this form, where dou rho by dou t plus dou by dou x, dou uj by dou xj equal to 0. These are written in the initial form. So we see that this uj and this xj, this j and j index are repeating. So this is the scalar equation. In the momentum equation, first term there is indices I, and the second term also only indices I is the one which is not repeating in all the terms. So this is the vector equation. In the third equation, there is all the indices are repeating, whichever is given. And similarly, there is equation in the integral form are also given. We wanted to find the equation from integral form to this differential form. We have to use the Gauss divergence theorem. From Eilerian to Lagrangian form, we can find using the substantial derivative. Similarly, for this finite control volume form also, if we wanted to find the Lagrangian equation, we can use the Reynolds transport equation. There is one more equation called Reynolds transport equation, which generally is for this substantial derivative in the integral form. This can be written as for the this in the integral form. Now we are moving towards the small perturbation equation. We will see what is the rotational flow. The rotational flow is del cross V equal to 0. So as we have seen that for rotational flow, del cross V equal to 0, and from the vector identity we know that del cross del phi equal to 0. And so this velocity can be written as the gradient of one scalar field. This is called the velocity potential. So velocity can be equal to dou phi by dou x phi ei, and it is nothing but ui ei cap. So ui can be given by dou phi by dou xi. We have seen this velocity potential equation before. This is for the 3D. This is the continuity, and this is the momentum, and this is the sonic equation, sonic speed equation. This equation is for irrotational isentropic compressible flow. So if we write this equation in the 3D, we get the equation like this: 1 by 5 x square upon a square 5 xx plus 1 by 5 y square upon a square 5 y minus 2 5x 5y upon a square 5xy equal to 0. This is velocity potential equation, and another is a square equal to v naught square plus gamma minus 1 by 2 v square equal to a naught square minus gamma minus 1 by 2 5x square plus 5y square. This is the sonic speed in 2D equation. There are two boundary conditions. One is the body boundary condition. On the body, the velocity normal to it should be 0. So this is the boundary condition for that. And for the far field, velocity should be equal to free stream velocity. So now we will see the small perturbation velocity potential equation. So this is for slender bodies with a small angle of attack. So for finding the equation, we have to give the perturbation in the velocity. Our phase stream velocity was v equal to v infinity and v equal to 0. So we have given the perturbation, so it will become v equal to v infinity plus u cap and v equal to v cap. And our phi can be given by v infinity x plus phi cap. Here, if we take the derivative of this, dou phi by dou x equal to v infinity plus dou phi cap by dou x. This is equal to nothing but u. So this we will get u cap equal to dou phi cap upon dou x. Similarly, dou phi by dou y equal to dou phi cap by dou y, which is nothing equal to v, and it is equal to v cap. So this was our velocity potential equation. We will substitute this phi x is nothing but this and phi y is this. Our phi xx will be dou 2 phi cap upon dou x square, and phi xy will be dou 2 phi cap upon dou x dou y, and phi yy equal to dou 2 phi cap upon dou y square. So in place of phi xx, we have to substitute this dou 2 phi cap upon dou x square. We can multiply this whole equation by a square also. So by multiplying a square we will get, and substituting this phi x, phi y, phi xx, phi yy and phi xy, we will get a square minus phi x is v infinity plus phi x dou phi cap upon dou x. This is whole square dou 2 phi cap upon dou x square plus a square minus dou phi y square is given by dou phi cap square, dou phi cap upon dou y square, dou phi cap upon dou y square, dou 2 phi cap upon dou y square minus 2 dou phi cap upon dou y b infinity plus dou phi cap upon dou x into dou 2 phi cap upon dou x square equal to dou xy equal to 0. You get this equation. Similarly, there is one sonic equation also. So what was the sonic equation? Is, if we see this equation, E naught square equal to a square plus gamma minus 1 by 2 pi x square plus pi y square, or it can be written as 2a square upon gamma minus 1 plus pi x square plus pi y square. A square is nothing but a infinity square. So we'll get a infinity square upon gamma minus 1 plus b infinity square upon 2 equal to a square upon gamma minus 1 b infinity plus u cap, sorry, this a is not infinity. So first at the free steam we substitute it, then it will become a infinity square upon gamma minus 1 plus b infinity square upon 2, and at some point it will become a square upon gamma minus 1 b infinity plus u cap whole square plus u cap square upon 2. Now if we this u cap also here this dou phi y dou x is nothing but u cap, dou phi y dou y is b cap, this is dou u cap upon dou x, dou b cap upon dou y, and this is dou u cap upon dou y. Or dou b cap upon dou b cap upon dou x. If substitute these and substitute the value of a square from this equation, we will get this equation. This is the exact equation. This is the small perturbation potential equation. For small perturbation, this u cap b cap will be very less than b infinity. This third term will always be very small for the small perturbation. The second term will be less than this dou b cap upon dou b dou y for infinity less than 5. It means for supersonic flow and subsonic flow. And this first term will be smaller than this term for Mach number less than 0.8 or Mach number greater than 1.2, because nearer this term this value will be small. So for neglecting all these for supersonic flow, supersonic and subsonic flow, this is not applicable for transonic and hypersonic. It is not applicable for we will get this equation. We can also find that Cp will be given for this minus 2 u cap upon b infinity. The acceleration surface with inclination theta, then Cp will be given by 2 theta upon under root n infinity minus 1. N infinity is the minimum for supersonic flow. And if there is expansion, then it will be given by minus 2 theta upon under root n infinity square minus 1. Now we will see what is the hypersonic small disturbance theory. So if we see the governing equation, this is for steady, this equation is for steady flow, and in this is isotropic. So in the general equation, if we do the scaling using this term, let's say there is a slender body with d diameter and L is its body length, and its slenderness ratio is tau. dy L is equal to tau, and free stream velocity is v infinity, and we perturb it by u cap, v cap, and w cap. And we write xy equal to xy L, yy equal to yy L tau, zy equal to zy L tau. Because mainly changes are happening in y and z direction. As in the x direction velocity is very high, there will be not much changes in the velocity, free stream velocity. So u cap will be very less. So by using this, we can find this hypersonic small disturbance equations. In this equation, we find that this in the first equation. If you see the first momentum equation, u bar dash is only present in this equation. Rest of the 4 equation it is not present. So first we will solve the rest of the 4 equation and find the unknown. After that only we will use this x momentum equation to find the u r cap. So this u r cap is decoupled from other equation, which imply that there is not much effect in the u r cap. We will also see what is the Newtonian flow. This Newtonian flow is the simplified theory to find the Cp on any surface. So according to this theory, if let's say there is one flat plate inclined on a flow and flow is hypersonic, then whatever momentum is perpendicular to the plate, it will be transferred to the body. Let's say this is density rho, and this is the angle theta. So change in velocity in normal direction is v infinity sin theta. flux normal to the surface is a component. Mass flux component normal to the surface will be given by rho v infinity, rho infinity v infinity a sin theta. Let's explain area A. So rate of change of momentum in normal direction, it will be equal to rho v infinity square a sin square theta, and this will be equal to force. So what will be the pressure? Fya equal to rho v infinity square sin square theta. In this one, this pressure, hydrostatic pressure is not considered, so it will be P minus P infinity. Pressure due to generally free stream pressure is not considered. So this Fy will be equal to P minus P infinity. It gives me rho v infinity square sin square theta. If you Cp is given as P minus P infinity upon half rho v infinity square, which will be equal to 2 sin square theta. This is called the Cp due to Newton's theory. So if you see also for the hypersonic flow, there will be shock wave which will be very close to the body, and flow will turn towards body, and it will be tangent to the body, and so almost full change for this beta. If you see shock angle beta will be very less, and it will be approximately equal to theta. So that's why in the hypersonic flow, the change in the normal direction, so almost all the velocity, all the momentum in the normal direction will be transferred to the body, which will give the Cp. Is there any question?
No.
Is there any doubt also in this week's lecture or last week's lecture?
No, I didn't start yet the lecture, as I said. I'm
Okay.
listening to it because it's to understand.
Okay. Generally, in the first week's lecture,
But
there was thermodynamics and compressive flow, basis of thermodynamics and compressive flow only. So it will be better to revision if you can do the revision for that.
Okay.
And the second week, there was some revision of vector, and only in last two, you can say last two lectures, it was mentioned about Nagre's equations and this small disturbance theory. So mostly you can see this week was focused on the revision, and only in the last part it was on this disturbance theory.
So today that's it. That's for the today.
If you don't have any question, then okay, I will stop for today.
Perfect. Thank you. Okay. Bye.